I'm very happy to introduce Nicolas Behr, who will today be telling us about double-categorical compositional rewriting theory. Take it away.
Thanks a lot, Bryce, and many thanks to you and Tim for the kind invitation. And as I was just saying to Tim, congratulations on this really nice workshop, and I hope this format will will continue in the future also. So today I suppose I'm a little bit the outlier in the program because I will talk in a sense about applied double category theory. So I'm a computer scientist at Université Paris Cité, and I will be speaking about recent joint work, I should say also in progress, with Paul-André Melliès and Zeilberger. And this work was based on previous work with Rassama and Jean Crevin. For this work, you can find fortunately a very long preprint on the archive, in which you can find a lot of background information and references. So, okay, maybe you should change the slide somehow. Let me give a second. Okay. So the motivation, I will speak about compositional rewriting theory. And rewriting theory is a concept in computer science, which is actually quite interesting because you can speak about manipulations of graphical structures. And sort of the very simplest level 0 example is that you have a finite set, or maybe you can represent it as a graph without any edges. And then a manipulation could be find two vertices in that set, take them out, and put a new vertex in. So that looks like an absolute toy example, but it is indeed, if you put some extra semantics, it'll actually encode a very simple version of chemistry. So it's already quite useful. And then nowadays, of course, there is a lot of work, especially recently in terms of COVID, for example, modeling the spread of diseases on networks, where these networks represent, for example, social communities. Like you could imagine, you have such a graph, and then this rule here says if you find a susceptible and a person who is somehow in interaction with a infected person, then it might happen that the susceptible person also gets infected. So this is already quite a large step in generalization, because now you're talking about some graphical structure, and now it really is. There's some relationships because of the linkage of vertices that is at play. And even more general, and now going much into mathematics, actually. So I learned in 2019 at a workshop at the RCS in a talk by Artemi Kislev about this kind of rule, which is used, it's part of this conservative graph cohomology framework, apparently. But really independently of that motivation, it is also interesting on its own right. It is an operation where you take a graph, you pick a vertex in it, and this is a finite directed multigraph, so this vertex has a certain number of ingoing and outgoing edges, say m ingoing and outgoing, and then you clone this vertex, add an additional edge, and repartition the original ingoing and outgoing edges between the two vertices, meaning that afterwards you have m1 plus m2 equal m ingoing edges and 1 plus n2 equal n outgoing edges. So these three very different examples at very different levels of generalization all fall into one paradigm of semantics. So if you want to formalize in category theory, what are these operations, you'll find that a rewriting step can be formalized for all these three examples in so-called double push-out semantics. So that's a concept which has about 50 years of history. Although we only about 2 years ago, we managed to understand how to do these operations like of this cloning of vertices type, but okay. And the idea is that the rule will formally be encoded as a span of objects, like input and output. And then the rewriting steps themselves, you see here, there's an X, that is this original object. You have to find an instance of the input pattern of the rule in X, usually through some sort of mono. And then you will form this little diagram on the right, which consists of two push-outs, hence the name double push-out rewriting. And of course, here in these three examples, you need to figure out what is the correct category, which sorts of embeddings you can allow for this to make sense, and so on. There's a lot of formalism, and as I said, you can find many details in this large preprint and references as well. But for the moment, it's an interesting observation. And of course, suggestively, this is a workshop about double categories. I guess you have already an idea where these will come up. But before going into that, let me tell you about something which, as mathematicians, maybe you might not be so aware of, but then again, you presumably know all of the ingredients, so that's quite fun. Because in computer science, we are often also interested in the combinatorics of such manipulations. So what do I mean by that? So going back to the set rewriting example, of course, this is very well formalized in combinatorial species theory. And in combinatorial species theory, if you want to count the number of objects you can have, it is very common to go into this framework of formal power series, so generating functions and such. And of course, on formal power series, let's say here for simplicity, just in one variable x, you have two linear operators, namely the multiplication with formal variable and the derivative. And then you can, of course, generate all the monomials by repeated action of this multiplication operator. I mean, the first thing to note, which is interesting, is that the monomials are the basis of a vector space of formal power series. These differential operators are then endomorphisms on that vector space. But more combinatorially speaking, if you now look at the action of q-fold derivation followed by p-fold multiplication on some monomial, there's a combinatorial prefactor. I mean, it's a non-negative integer, so it has a combinatorial interpretation. And indeed, it's exactly the number of ways to take q elements out of an n element set, I mean, without having an order on the q elements. And now if you look back at this example of set rewriting, there's this operation of taking two vertices out and putting one back in. And now here, this combinatorial prefactor arises. It's exactly what you want to count, like the number of ways disregarding order of picking two elements and then applying this operation. And so now this looks like just a coincidence. And there's a slightly more formal computation you can also do just with these endomorphisms. Namely, if you do a sequence, take out S elements, put in R, take out Q elements, put in P. And it's intuitively clear that of the Q elements you take out in the third step, some of them might have arisen by creating R elements in the second step. I mean, reading from the right, because we have to use the order of matrix multiplication here. And so you see here on the right-hand side of this equation, again, I mean, slightly more complex expression. It'll have some interpretation, but more importantly, it's a non-negative integer again, which we can interpret. And if I tell you that if you take these operations, taking a certain number of elements out, putting certain number of elements in, the right-hand side ranges over all possible composite operations. Like if you understand the over all four steps, but as a composite operation, you get exactly all the possibilities on the right-hand side with their combinatorial multiplicities. But I mean, what I'm saying here is hand-waving, yes? I mean, I'm telling you something from experience, like an empirical observation, that in this calculus of formal power series, there's something which resembles a little bit the combinatorics of rewriting steps. Of course, one wants to formalize this, understand it better. And so the goal of the work I'm going to present here is to not only understand these equations from category theory, but more importantly, generalize them to all of these various kinds of rewriting theories that can be formalized in categorical rewriting theory. And so the plan is, so first of all, hidden in what I showed on these linear operators on formal power series is this concept that you'll have a vector space over states. I mean, in the set rewriting case, if you only consider isomorphism classes, the state is labeled by the number of vertices. So here in general, we'll have a vector space indexed by isomorphism classes objects. And then the question is, how do you, I mean, you want to have a kind of operation, you somehow to a rule R, and in effect, you'll have to work with equivalence class of rules of some sort. So there's a delta of R. You associate an endomorphism over this vector space, rho of delta of R. And the semantics should be that in some way you range over all the possible ways to rewrite X into something else, R alpha of X, and that'll have some combinatorial prefactors. And so that is sort of the analogon to this equation. I guess what was the number? To equation 2 up there. Then the other interesting bit is this way of how do you get the states of your vector space? So these kinds of vector spaces all arise by acting on something like an empty configuration. repeat with some generators. So, and these generators will be arising from rules from this. I mean, it'll be a strict initial object into this object X. And so that has to be expressed somehow. And I mean, the most complicated bit is that somehow, if we have rules acting in one past the other, you can imagine there's again this idea that these rules can interact. And we want to express this interaction. We want to count the number of ways you can interact to get a certain composite rule. And so that is this equation 3. And again, there are integer, non-negative integer prefactors that can be understood combinatorially. And the highest level of the formalism is to be able to formalize this equation 3 using some algebraic structure, which I call rule algebra product. And I should say, I mean, these equations here, you can, I mean, I've previously worked already with category theory to, of course, formalize these rules and their compositions. And I've developed a formalism for these rule algebras, which maybe was not formalized to the very last end. And so this work here is really now the attempt to give a full formal meaning to these kinds of operations. So the essential obstacle here is, and you, of course, I mean, you are category theorists, I suppose, many of you, so this might be trivial to you, but it's a huge obstacle in the algorithms. So all of these concepts we use to construct our writing steps arise from universal concepts such as push-outs, for example. And I mean, a push-out, of course, is such a commutative square which satisfies this universal property. And so the key difficulty in, I mean, if you imagine you form all of the possible rewrite steps, but that is a hand-wavy thing because, I mean, if you construct a push-out, what you really want to do is you want to pick a representative for the push-out in an algorithm. I mean, imagine you have set rewriting. If I form a push-out of a monic cospan, of a monic span, then somehow I mean, my algorithm should pick a representative for the set union. And I mean, at the very least, you have the problem of choosing the right labels. And so if you imagine now counting these things, you have to make sure that you have some sort of consistent system of picking representatives for the universal constructions. And that really complicates things a lot when you want to reach a formalization of, you know, not only these rewriting steps, but counting them and counting their compositions. So that I should say that with Paul André and Norm, I mean, we have thought about this for about 5 years now, and it was only very recently that we found a way of, you know, finding a satisfactory formalization, I think. And so just before going into the main part of the talk, because I think it's nice to have a good example, so let's briefly look at what is double push-out rewriting for sets, for finite graphs with just vertices. So here's again now formally this rule that takes out 2 vertices and puts in 1. You see it as a span at the top. These things reach from right to left because we want to be consistent with the order of matrix multiplication later on. Yes. Here at the bottom right, you see an original graph of 3 vertices. And then here's one particular way to pick 2 vertices. You remember, like push-out in finite sets was computing set union effectively. So if the intersection is empty, then you try to find a set C in the picture on the right side that you know, together with the other leg gives you by push-out the graph. So effectively, this is called a set complement then, I guess. And then you have to disjointly join to get the left push-out. And voila, indeed, you have taken out 2 vertices, kept 1, put another one in, so you reach 2. I mean, just to have a concrete picture, because things will get very abstract from here. Okay. All right. And so here's a plan. And so again, like we want to reach some notion of formalization of linear operators acting on some vector space. We want to get interpretation of these combinatorial factors. And the strategy that after a lot of trial and error proved fruitful is the following. So, I mean, as you already guessed, the cells, the individual writing steps will be the 2 cells of a suitable double category. But the more sort of non-intuitive bit is to go into a categorification in order to retrieve these non-negative integer coefficients. And I mean, in the sense of Dolan, for example, a categorification often a problem which involves endomorphisms and acting on some vector space would be that we will try to produce a calculus of certain types of sets of which the cardinalities will reproduce these non-negative integer coefficients. And you will see how this works in the talk. I don't think I can describe this better for motivation here. And maybe even for you as mathematicians, what might be nice to see is that this particular application of double category theory has a nice mix of concepts involving, besides double categories, of course, presheaf calculus, some vibrations, some coends, and multisums and other constructions. So yeah, okay. So let me start with the main part of the talk. So I'll just fix some notations for double categories, and I mean, I realize I guess they are like a 90-degree clockwise rotation of the conventions I've seen Mike Schulman's paper, for example. So maybe just to be sure. So we have a category D0. That'll be the objects we are going to rewrite and with which we, will eventually formulate rules. The vertical morphisms are typically some sort of monomorphisms, which I use as hook arrow notation to remind. And the category D1, the objects will be precisely these rewriting rules. So in the cases of double pushout, for example, this will be some sort of spans. And here you are, and the nice thing about double category theory already here is that for the spans, you can use arbitrary morphisms typically, while for the vertical morphisms, you are forced to use some particular kinds of monos typically. And then the cells, the two cells will be the rewriting steps. So imagine the double pushout cells. Now I use the notations S and T, I mean, for the horizontal and source and target, and the notation U for this embedding of D0 into D1, which is effectively produced from a vertical morphism, a horizontal identity to cell. Vertical composition, I mean, just to remind, for me, the vertical composition is a strict direction, yes? And it just arises as a composition of D1 then. But the interesting bit is, of course, the horizontal composition, which in general will be only weakly associative. I mean, typically because you do something like composition of spans here. All right. And here, I mean, I should say throughout the talk, maybe afterwards in the discussion, I would be quite grateful if we are doing some weird notations and there's some better ones to, of course, learn about this, because again, I'm not a mathematician. But we fix this kind of idea of an unbiased presentation for the double category purely for notational convenience. So there are these functors Hn, which map from a sequence of composable horizontal morphisms or horizontally composable two cells into the composite. H0 is just this, embedding of vertical morphism into identity two cells. H1 is the identity, H2 is the horizontal composition. And then we have this convention that Hn plus 1 are some functors, which are isomorphic to sort of a, I guess, lexicographical order of horizontal composition. The only reason we pick this is so that in pictures later on, in depictions of two cells, we can make sense of what it means if a two cell has a horizontally factorized boundary. It is always meant that then in that case, the meaning of that diagram is that you, actually have a two cell between Hn, the composite of the boundary, and the other boundary, just to be able to save some notation, white space. And the paradigmatic example, actually the running example of this talk will of course be double pushout rewriting. So again, to remind, the horizontal morphisms are spans, arbitrary span of your underlying category. Vertical morphism will be some sort of monos. And then a composition, and here you see that, well, this composition involves pullbacks of spans, which of course then have to exist. So that's one requirement for the ambient category. And then in order for, in this operation to produce, in this cube, that the outer faces are also then really push outs and so on. You'll have quite a long list of axioms to ask of the categories from which you build this double category. And you can find all of those in for example, our long preprint. I'll not go into this here. We'll just assume we have this composition. But it's satisfied for most interesting examples of rewriting. Okay, so that was the easy part. And now there's this nice idea which my co-authors came up with, Paul-André and Norm, that in a double category, it's often interesting in computer science to look at presheaves, actually covariant presheaves over the D1 category. And we'll reserve the notation capital delta hat R for just the covariant home functor from R. R is an element of this D1. And so the very first attempt one might have, so if we want to count number of ways to rewrite, would be just to take this covariant presheaf and then apply it to some x goes to y, and then count. I mean, take cardinality. I mean, this unfortunately doesn't work, and this puzzled us for a long time because you will basically overcount. So the point is, the rough idea is that you have this rule R, you have an object X, you ask, can you go into Y via some rule, rule S? But unfortunately, this double push-out construction is very symmetric, and you'll typically overcount all of the essential isomorphisms. So that doesn't work at all. It's really giving the wrong result. And so we are still at this level of now we have an idea how to categorify maybe these row of delta of R that should be somehow related to this delta hat of R. But then how would you define a composition? How would you create from the vacuum? How would you get to these integer coefficients? So this is really, at the moment, this is a too simple idea. So how do we proceed? And there's one piece which is relatively straightforward, and all of these cases of compositional writing we usually have, there's a notion of empty object, which technically speaking must be a strict initial object of the D0 category. And then because really all of these things interact nicely, we ask some property, I guess, which roughly says that in the horizontal category level of objects, for each object X of D0, you have exactly one horizontal element from the initial object to X and from X to the initial object. And then there is some other condition on two cells, namely that there exists at most one two cell between any two such special shape of D1 objects. And actually, if anybody had like a nice idea of what this means in double category theory, maybe it would be nice to discuss later. In any event, so now the point where we started to see that this might work in some shape was when considering coends. And here I'm just recalling the formula for coends over profunctor, which is in a sense just a nice way of saying index disjoint union, basically of f applying f diagonally. And the equivalence relation here, of course, is also created in some shape by this profunctor. And now, if we use exactly this formula, we just simply apply it to now n different such covariant presheaves over D1. We can define what's called the convolution product. So it is some notion, it's essentially a generalization of Day convolution, I guess. It's a left Kahn extension of the Cartesian product of these presheaves along this. So Hn was this functor which allows to horizontally compose sequences of n composable cells. And if one parses out this definition, one finds that if you symbolize what are the elements in this set, if you take an element R and apply this functor, you get diagrams of the shape on the bottom right. You have a sequence of composable morphisms S1 to Sn. Over each Si sits an element of the respective presheaf, and then there is a mediating two-cell sigma that finally goes into this R. And if one wants to look at what is the equivalence relation, so here's just the generic formula. But okay. I find it personally nicer to look at what it means in terms of these diagrams. In terms of these diagrams, it means that if this mediating two-cell at the foot really arises as some morphism tau vertically composed after the horizontal composition of n-fold, of a horizontally composable n D1 morphisms, then you can absorb essentially this morphism, the elements of A, into the presheaf. And so essentially you can push down the joint foot of these little roofs if you want. Okay, so again, like we are inching a little bit closer to what we wanted, because if you evaluate now this convolution product formula on these, you could say these Yoneda distributions that I had, you get shapes which are exactly n-step sequences of rewrites. So you take an original object at the bottom right and you rewrite it in n steps. But unfortunately, again, it is not quite what we want, because there's still this mediating cell sigma. And this idea to use convolution products arose a few years ago already, but unfortunately, this still, I mean, it's even further away from what we wanted to compute than just an individual counting individual writing steps. And so far, on the other hand, we haven't used really very much theory. We have just used like a vanilla double category theory, if you will, and coends and so on. And it's really now that the interest, I think mathematically interesting parts of the story arises. And this is, I mean, the story of this part of the construction is that when we started to finally understand how to do double push-out rewriting for these funny cases where you clone vertices and so on, this gave like a very complicated way of composing rules. And then when trying to understand this, I mean, I sent out a preprint of last year's conference paper, amongst other people, to Richard Garner, and then he had this very nice comment on vibration. Some of our constructions seem to remind him of vibration. He had very concrete ideas about this. And then I looked deeper into this theory of vibrations. It was very interesting. And finally, this pushed us towards taking that seriously and trying to find out which vibrational structures are relevant for us, really. So the original construction of Grothendieck-Orff vibration, I suppose, quite well known here in this field. So you have a functor G between the fiber category and the base category. And essentially, being a Grothendieck-Orff vibration means you can lift a morphism in the base. It's so-called Orff-Cartesian lift. And then if you have any other, basically you have a sequence of morphisms in the base which lift to a morphism epsilon, and you have a Orff-Cartesian lift over F, then you can uniquely fill in this diagram. There exists this mediating morphism in the fiber. It's not quite what we need for our constructions. I mean, we actually will need 3 variations of Orff vibration. So the first one, I guess also very well known here, is the street Orff vibration. So it's almost the same as a Grothendieck-Orff vibration. The only difference is that a lift of a morphism in the base can, in general, only be done modulo a mediating isomorphism from here, from B prime to B tilde. But I mean, then the Orff-Cartesian property, the second part of the equation, is the same as in Grothendieck case. So that's very nice. Then we need another flavor of generalization. And roughly speaking, the generalization is that lifts might actually fail to exist, or there might be many inequivalent lifts. And that is exactly what happens. Actually, you will see later in the writing case. And now also the meaning of the universal property is slightly different. You take a factorization of, I mean, a sequence of morphisms in the base that lifts to a morphism in the fiber, but you do not yet require already to sit a lift already over F. That's a crucial difference, it turns out. You only say that if you have such a sequence, there will exist an index J in this family of lifts, such that there's a lift and there exists this unique mediating morphism. And then the price of having this generalization to possibly these families is that you have to explicitly say how liftings are equivalent. And that's the second part of this equation. And finally, most Baroque version is in a sense a synergy of the 2 kinds of generalization, where, I mean, effectively it's a similar idea as in the street case, that the liftings are not directly over the morphism in the base, but modulo some slight extension of the morphism in the base. And in this residual multi-Orff vibration case, which we introduced for working with these compositional writing double categories, these morphisms, these residues might not even be isomorphisms, yes? So that is sort of the most general version we have. And I already shared the slides, so I mean, I won't go into these details here, but that's in any ways our definition. Okay, and then now one nice thing I learned from reading about vibration theory is that there's this idea of cleavage, and it's essentially a systematic way of picking lifts. For these Grothendieck and street Orff vibration, I guess it's very standard. For the multi and the residual multi versions, picking a cleavage amounts to fixing, I mean, lifts are unique up to universal isomorphisms and amounts to picking one representative per class. So I mean, it's slight generalization, it's a concept for the Orff vibration cases. Okay, so let's assume we have such a cleavage. And now the first point, I mean, so the first of the 3 kinds of generalizations of vibrations, the street case, arises for if we study more closely what extra properties do have these horizontal composition functors here for the case of composing two horizontally composable cells? And it's really funny that they I mean, we in this preprint you'll see we had a condition which was just describing the axiomatic structure we need, but you can actually formalize this as a particular kind of street op vibration, it turns out. That's a new result now. It's not only a street op vibration, but it has one extra interesting property, namely, I mean, I find it more easy to read the explicit formulation at the bottom. So if you lift, if you have a two cell of which the top boundary factorizes into a sequence of two, I guess, horizontal morphisms, then you can split this up into two horizontally composable two cells, modulo an isomorphism. But this isomorphism on top is, I mean, if you want, globular. I mean, it's not basically the vertical morphism of the cell are just identities. So I would call this, just for having a name for globular street op vibration. And then you can show by induction, the way we defined this Hn was somehow inductively from repeated application of H2 in some shape up to ISO. You can show that also the Hns are all globular street op vibrations. So that's nice. And I mean, I say that we found this. What I mean is we had our concrete examples, the classes of examples for rewriting theories, and we found that this is actually a property they satisfy. So it's in a sense an empirical result. There's another structure that is satisfied for all compositional writing theories, namely that D0 has so-called multi-sums. What that means is that for any pair of objects of D0, there's a family of co-spans of D0 morphisms, such that any co-span starting from the two objects will factorize through an element of this family in the shape. And the universal property is that any two factorizations will be related by a morphism, which means again that, I mean, elements of this family are unique up to isomorphism. So again, we can pick a cleavage, so one co-span per equivalence class to simplify matters. Okay, and then the other interesting bits is I had two more generalizations of op vibration. So one is this multi-op vibration. It turns out that the horizontal source functor on two cells has this funny property that if you have a vertical composite of morphisms as a source, a horizontal source of a two cell, then you can uniquely split up to universal isomorphism, you can split up this cell into a vertical composite of two cells. Then there is the target functor, the horizontal target functor, and in the most general examples of compositional writing double calculus, this will be a residual multi-op vibration, which means that if you want to split vertically a two cell of which the target, horizontal target factorizes, you can do so, but only modulo a small residue. So it's not directly at the codomain of what is called N, but you know, with a certain extension. So these are now the properties we have to play with in the full example of compositional writing theory. Now let's see how this helps, and this is really it's a very recent result we have, because we were stuck in a way at this point at looking at this generic definition of convolution products. It almost looked like somehow encoding sequences or writing steps, but not quite. And now that we have this additional information that these functors Hn are globular street op vibrations, we can actually evaluate normal forms for these equivalence classes, which have like computational meaning. And what I mean by that is if you take any element, any diagram of this shape produced by this coend, at the bottom sits this mediating cell sigma. So we now use the globular street op vibration property of Hn to split the cell up into horizontally composable sequence of n two cells, modulo globular isomorphism at the bottom. And now, parsing out the exact definition of the equivalence relation, we can absorb these horizontally composable two cells into the presheaf, and we reach a configuration which no longer has a mediating two cell. And this is exactly the shape of things we want to count. And so concretely, The remaining degree of freedom, if you wish, of the equivalence relation is just by globular isomorphisms. And if you now parse out the definition for the concrete case where each of the presheaves is one of these Yoneda presheaves over a rule Rj, then we get shapes of diagrams which are exactly now sequences of rewrite steps modulo precisely those degrees of freedom, namely all these universal isomorphisms quotiented out by the equivalence relation. And this is exactly what we want to count. So here's the first point where we succeeded in providing a categorification, in this case of the idea of counting n-step sequences of rewrites. So that's quite nice. And now this is almost what we want, because we also had this idea that in the decategorification, if you take cardinalities, we wanted to produce the, if you wish, the matrix elements with non-negative integer coefficients. And for that to work, we have to check one more thing, namely that this convolution product is weakly associative. So, because I mean, later in the decategorification, the matrix products will of course be strictly associative. And what that means is that we have to check, or I mean, one could check it another way, but we found out that the easiest way to prove this is to go from the nested two-fold convolution product directly to the threefold convolution product. And so how does this go? So evaluating out the generic formula for F3 convoluted with the convolution product of F2 and F1, you get a shape of diagrams as so. And now there's two equivalence relation acting on this, one from each coend formula. So in the first step, you take one of these generic diagrams and now use the globular street op vibration property on the bottommost cell. You get this second diagram in the second row, which then by the V type, I mean, the V equivalence relation is the one arising from the coend over these V1, V2 type morphisms. You can basically absorb this split into the presheaves. So on the right-hand side, this gets an extension of the foot of this V-type coend. Then you again apply the street op vibration property of H2 to split. You absorb, and in the very last step, you simply compose out the two cells at the bottom. I mean, using whiskering, I guess. And this already looks very good. This is generic element of the triple convolution product. The only what's left to check is that you can emulate the action of the global. I mean, the degree of freedom is for the triple convolution product is by globular isomorphisms. And indeed, if you have such a generic shape of the triple convolution product, you have this horizontally composable cells which are overall giving a globular isomorphism. Then you can first simply compose out the first and second from the right two cells to get this blue curvy two cell, which is again an isomorphism. You then use the V-type equivalence relation to absorb it into the presheaves. Then you are left with two cell composable on the right. You absorb that into the presheaves, and then you simply forget that what is called T1 and T2 prime were composed, and voila, you have exactly the shape that you should have for the action of globular two cells in the triple convolution product. And we have thus proved that indeed F3 convoluted with F2 convoluted F1 is isomorphic sets applied to an R to the triple convolution product, and then analogously you can do the other direction. So this completes one part of the program, and now we are left with sort of the highest level of the framework is we not only wanted to count sequences, but we want to find an algebraic structure that expresses the interaction of rules and sequences, much like in this calculus of formal power series. And so the idea is as follows. So for the two-fold convolution product, I mean, recall that it encodes sequences of two rewrite steps modulo universal isomorphisms. We will find that using now all of the vibrational structures and multisums, that you can alternatively recover the set of contributions as a disjoint union over this complicated looking formula. So it involves multisum elements, residual op-Cartesian liftings, and op-Cartesian liftings. And that'll be the definition of rule algebra product. So I'll show you how this arises and how it uses vibrational structures now. So on the left, I show a generic element of the convolution product of two Yoneda presheafs over rules. In the first step, so this multi-sum property means that any cospan, and here I'm splitting the cospan from the codomain of R1 with the domain of R2. I can split this using this multi-sum property of D0, getting this orange cospan, the mediating morphism. Then I do a residual multi-op-Cartesian lift to split vertically the right-hand cell, recalling that the target functor, the horizontal target functor, is residual multi-op vibration. And then I use, I get this residue, and then at the level of the residue, I split vertically the left two cell to get this configuration. And finally, I just compose out the bottom two lines of two cells, yes, to finally get a shape of this form. And this is exactly one contribution to this disjoint union I showed before. And conversely, whenever I have such a shape, I can simply use the globular street op vibration property to split this mediating two cell at the bottom, and then vertically compose cells to get to a configuration on the right, which, as you can see, is an element, a generic element of the convolution product. Yes. And so in a way, I can characterize elements of twofold convolution products through these kinds of shapes where I've exhibited the multi-sum element. And now, much as in the proof of associativity or weak associativity of the convolution products, I can show, if I call R2 O dot R1 exactly this set of all possible ways to overlap the rules and produce these shapes, then I can show again by the strategy of passing through triple convolution product that this O dot operation is weakly associative, I guess. And so in this way, I've found a categorification of the idea of interaction of rules. And I think this is very abstract for the second, so let's directly dive into an example. So if you remember in the beginning, I had this funny case of rewriting where I take a vertex, I clone it, I add an edge, and then I repartition the edges into it. What's beautiful about categorical writing theory is that the power of these universal constructions, in the sense that the rule in this formalism is just really expressed as on the top right, take a vertex, reading it from right to left, split it, and then, by splitting, I mean that the right-hand side is an epimorphism that merges the two vertices, and then add an edge. So one can imagine now asking, if I act with this rule and another time with the same rule, what are the possible ways that things can interact? By interact mean that I touch with the second application of the rule something which was already acted upon or created by the first rule. And the interesting thing about this new formalism is that now with this categorification of the rule algebra product, all we have to do is simply list representatives of the diagrams that I can produce using the multi-sums and residual multi-op-Cartesian lifting. So, sorry, can one see the mouse? Yeah, okay. So, this might be a bit confusing, but I just go through a few cases. So here you have one rule and another rule always. It's the shape of these diagrams. So the way I construct these diagrams is as follows. I first take a multi-sum element. So how this works intuitively in this case is you have to overlap a vertex, partially overlap a vertex and a graph which has two vertices and an edge. So either I do not overlap at all, that's one contribution, or I overlap on one of the vertices, or I overlap on another of the vertices. And the indices are just helping to say what overlaps with whom. So in the first case, I do not overlap at all. And now I have to form this sort of multi-push-out complement. In this case, there exists only one contribution. You propagate, you then take push-out. And in this direction, there also, in this particular example, exists only one representative. So I take push-out complement, I push out. The intuition with push-outs is that you glue together, if you can visualize this. objects that I mentioned in this span, with the overlap being the apex of the span. So here in this case, you just produce the parallel application of the two rules, and overall this gives a shape like this. But then when you start now, if the second rule attacks the verdicts that you have produced via the first rule, so this is, for example, the case here. If you now take this multi-push-out complement, or like this multi-op Cartesian lift to the left, you now have to decide where you put the edge. This is exactly this redistribution of edges. I mean, there's one edge here, and you have to say whether it goes to the first or the second copy of B when you clone. So these are exactly these two options here, and then you take push out, you just glue together. And so this gives overall, because you have two ways to non-trivially overlap the vertex with the output graph here. And then for each of the ways, you have two ways of redistributing this one edge. So overall, you exactly get 4 options. And this is, and moreover, you can look closely and you find that 2 of the options produce like a sequence of 2 edges overall. And the other 2 options produce a sink or source. And the beauty is that now really we have a guarantee that when we, like for example, in this nice algebraic rewriting.jl framework from the Topaz Institute, if you implement rewriting rules just at the level of these diagrams, as long as you are careful to pick representatives for each universal construction, you can precisely recover the combinatorial prefactors through simply taking set cardinality, and of course taking account that in the end you are just interested in the composite rules. For that you then basically get multisets. But we can recover now these combinatorial factors. That is the surprising thing. And I just want to mention that there is also now a way of coding this idea that somehow acting on a basis vector, which is for an isomorphism class of objects, this is nicely formalized by this trick that actually the vectors of that vector space are generated by acting with endomorphisms associated to generating from strict initial object that rule. And indeed, so if you now compute the convolution product of a rule that creates X from the strict initial object, and then the rule R applied to that, you can check whether an object Y can be produced in this way simply by using the multisum, by using this convolution product formula. And if you parse out the details and use it as this multi-op vibration thing, and the strict initial object has this nice interplay with the double category, you can manipulate this with equivalences to show that indeed you are exactly counting rewrites modulo universal isomorphism. So this is exactly the thing we wanted. And just as an outlook, now that we have the intuition to work with coends to compute things, you can go one more step, and you can also reproduce something which is known in combinatorics, namely this operation where you try to count all ways to rewrite an object. I mean, regardless the outcome. Evidently, I should say that in all cases, our categories are finitary, so objects are finite size in a way. And so this is just possible by taking now a coend over the D0 to basically take the y's up to isomorphism, it turns out. And in this way, we can precisely now produce a number of ways to write X with a rule to any object. And that is also a nice operation one can do. So we have a very comprehensive way of starting to do combinatorics now. And I just wanted to mention, I think I'm pretty much exactly reaching the end of my time. So one of the motivations of this particular team and my other collaborators was that we will start a large collaborative project in March 2023 with a team of about 20 experts here in France, where we will construct something like an analog of the NLab, but with formalization in COG, and this proof assistant enabled. So in particular, this will be a collaborative platform where you can, you will be able to edit something, the wiki articles, but also directly access COG from the web browser through it, and many other projects. The purpose of this platform will be predominantly to have a nice Wikipedia type account of compositional writing theory. So, but since, as you see, there's a lot of double category theory involved and many other concepts from category theory, effectively, I guess this will evolve into some sort of NLab-like platform. So if you're interested in following this project. We have a web page already, which for the moment just leads to some seminars we did. And maybe you can check in back in March next year, when hopefully we have a prototype of this platform available. And of course, I would be very interested in your feedback, particularly on the double categorical aspects. And with that, thank you very much. And once again, thanks to Bryce and Tim for the invitation.
All right, thanks, Nicolas. Okay, so are there any questions for our speaker? Maybe a question that I had is that I guess you're interested in the combinatorics, right, and the counting of these things. But
yes,
I've also imagined that's like it's too hard to do by hand. This count, like you showed us an example where you could do something, but like, have you got a way to implement this in a program that can count these things efficiently for you, or like how do you actually do the counting in the end?
Yes, so indeed, I mean, one of the motivations for this particular kind of formalization was that James Fairbanks and Christopher Brown are currently working on this algebraic rewriting .jl Julia project.
Okay.
And they came to ICT, the International Conference of Graph Transformation, this summer, and showed us the current status of this. And it is indeed the case that they implement currently the composition of rules. And so for this reason, it was quite interesting to see. So, I mean, basically, if you implement an algorithm, at which steps do you have to be careful not to overcount, in a sense? So, I mean, it is not simply that you take partial overlaps. I mean, you have to be careful how you perform the quotient, because you don't want to basically cut away options that are really essential. and so in all of this surroundings, we were starting to think about, I mean, what's the proper formalization? Because I guess the angle of this project is to use category theory all the way down to the very last moment where you then have to have a concrete algorithm to do multigraphs, I guess. And so there are currently some experiments going on, not yet for the full-fledged framework, but I think currently it's possible to do multigraphs and with rules that don't clone or fuse vertices. And yeah, and I mean, hopefully we'll be able to also get to these interesting cloning and fusing of vertices sort of things. Yeah. No, but I mean, doing this by hand, I mean, the main problem is that doing this by hand introduces errors, and also, I mean, real life examples are much bigger graphs even for the rules. So
yeah,
no, the idea is exactly not to do this by hand. Yeah.
Okay, thank you.
Thank you. Do you think I could ask some questions? Sorry, this is maybe the wrong way around, but
no, I mean, you're welcome to.
I mean, I wonder if I could take advantage of
I can't promise answers, but you're welcome to ask. Yeah.
I'm really sorry. This is a bit. It's just that because sorry, let me try to. Can I go back? Yeah, I hope so. I mean, because we are currently finishing this draft, and then I mean, there was okay. So I was wondering if anybody in the audience. Sorry, this is the wrong side. Yeah, I mean, I mean, it's a small technical point, but I'm just wondering if anybody in the audience might be able to tell me if this is something known in double category theory. So if the D0 category has a strict initial object, that there's this nice interplay with the D1 category, namely that for each object X of D0, you have exactly one element of D1 of this shape. Initial object goes to X, or X goes to initial object. And then also the second condition, that if you do have any two cells between such special horizontal objects, then at most you have one. Is that anything that is known or has a name?
I mean, have you compared this to what, like an initial object in a double category?
So that would
I mean, so there's this theory of limits and double categories and so on, and you can talk about, you know, initial objects and terminal objects and double categories and so on. And you know, you can define what an initial object and a double category is, and maybe it's worth sort of reading that, comparing to what you have here and seeing if there are some differences or if it's the same thing.
Exactly. So if you could maybe send me a reference, that would be very nice.
Yeah, I can do that.
Thank you. All right. Yeah, and the other question was whether in double category theory people have already thought about, I mean, when you have vibrational structures over the canonical boundary functors. Is that something you have seen in the literature? I mean, you as in the audience.
Hi, maybe I can say a little bit.
Hello.
That here. So that I'm giving a talk later this week about 2 ways of having growth and deconstructions and vibration notions that come with that. I think that what you're doing is not exactly the same as what we are doing. So I was thinking for myself, I've made a note, like, read these slides carefully. So to kind of look more carefully as to whether we can find some common ground there.
Yeah.
So I was wondering, maybe we can try to schedule some time next week or so to talk further.
With pleasure. Yes, please. Yes. In which time zone are you currently?
I'm in Halifax, so it's
okay.
5 hours from Europe, so to say, as far as time difference.
Excellent. Yeah, I'll send you an email, so that would be
okay. Perfect.
Thank you very much. I wonder if there's any. Excellent.
Okay, well, maybe if there's no other questions, we'll thank our speaker again.